Okay, guys, so I've tried to do this a couple times and had some technical difficulties, so I apologize. Um, Example 6.2 says towing a car up a hill. So a car with a weight of 15,000 newtons is being towed up a 20-degree slope at constant velocity. Friction is negligible at this point. The tow rope is rated at 6,000 newtons maximum tension. It wants to know, will it break? All right, so we have this blank slide. In a situation like this, I'm just going to say that it is always a good idea to draw a free body diagram. So we know that the car is going at an angle of 6 degrees, 20 degrees. Yeah, that's what it said. And remember, the car itself is going to have a normal force that's pushing upward, and it's going to be perpendicular to that x-axis. And remember, the x-axis we can change based on the incline. So the thing, though, about that is that gravity is still going to pull straight down, even though that doesn't look very straight down. That's what it is supposed to show. And this angle and this angle are the same. So since this is a 20-degree angle, that is also a 20-degree angle. Okay, so some other things that it gave us is it said that it had a tension of 6,000 newtons. Well, that was the maximum. And it also has that, let me read this question again. It says that the weight of the car, yeah, that's right. So the weight is equal to 15,000 newtons. Okay, yeah, that's all the information that it gave us so far. All right, so we've got a tension pulling this way, and we've got the force of gravity that's pulling down like this. So again, we kind of do like we did in that really long one before, where we can say, all right, there's a tension that's going in the x direction. And we're basically just going to write all of our forces at this point, even if they're not going in the x direction. So we have a normal force, and then we have force of gravity, and everything's equal to 0. And same thing for our y. And then we can start, after that point, we can start to figure out if, things are negative, or if they even have an x or a y value, depending on where they are. All right, so as far as the tension is concerned, that's that one right there. It is straight on the x-axis. So it's all on the x-axis. For the y, it would just be 0. A normal force in the x-axis, normal force is going like this, and that is our y-axis, so it's 0. Normal force in the y direction is whatever it is. And then the force of gravity in the x direction. Now that's the thing about gravity when it's on an incline, because now it does have an x and a y value because of this angle. So you can see that this angle right here is adjacent to the y-axis. So if we're talking about the x value, then that would not be cosine now, because it is adjacent to the y-axis. It would be sine. And also, looking at the placement of that vector, it is in the, it's going down. It's in the negative x over here, like in this area. So we've got negative force of gravity sine theta. And then we also have in the y, so we have negative force of gravity cosine theta. All right, so we've got some things listed out. So if we separate it out into x and y, So we have for our x, so basically I'm doing this one. I have tension minus force of gravity sine theta is equal to 0. If I was going to do for the y value, I would do normal force minus the force of gravity cosine theta is equal to 0. Okay, so we're going to solve for this tensional force. That's what we're going to see if 6,000 newtons is if it's going to break, if it's going to be over that. So if we're going to solve for tension, then that means that we need to move this over. So I have then tension is equal to force of gravity sine theta. Well, do we know the force of gravity? Well, we know that weight is 15,000 newtons, and we know that the angle is 20 degrees. So whenever you put that into your calculator, you should get 5,100 newtons. Well, if that rope can hold 6,000 newtons, will it break? No. Will not break. Okay. So example 6.2, I think is a little bit easier than example 6.1, but it's a good one because it does that incline. So we don't need that slide. All right, so then quick check 6.3, it says a car is parked on a hill, which is the correct free body diagram. Okay, you have to remember that this chapter is basically getting into friction. So we've got this car and it's just parked on a hill. Okay, so we have to figure out which is the correct free body diagram in this situation. Well, if it's parked, then that means that it is experiencing static friction. Okay, if that incline was, so steep that the car couldn't, stick on there, then it would roll forward. But right now, whatever the tires to the road, it's okay, it can stick there. So the static friction is an opposing force, so that means it's going to be going the opposite way that the car would roll. All right, the car is not rolling, it's not going that way. We know that there's a normal force that's perpendicular to the surface, and the thing about gravity is that it always goes straight down. So in that case, that would show you that C is the correct answer for that. Okay, if we were looking at quick check 6.4, it says that a car is towed to the right at constant speed, which is the correct free body diagram here. So it's going at a constant speed, which means that it is in equilibrium, correct? If it was accelerating, then we would have a net force. But in this case, our net force is going to be equal to 0. Well, which of these free body diagrams is showing a net force equal to 0? We know that there is a force that's pulling on it. We know that there is some sort of friction that's opposing it. We know that it's going up because of the normal force and down because of gravitational force. So our answer in this case is D. All right, so just a reminder of Newton's second law. We know that acceleration is equal to the net force, and just the reason that we say net force is that it's not always just going in one direction. Because of friction, we can have something that's opposing it. We talked about all of the different types of forces in chapter 5. There could be static friction, kinetic friction, rolling friction. There could be drag, from air resistance. So there are lots of things that it could oppose that, which would mean that you would have something like this. You would have like a positive force minus some sort of frictional force. Okay, and then that's divided by whatever mass you're talking about. And then it goes on to say that we can determine the acceleration by using kinematics. So that's where we kind of have to remember some of our kinematics equations. So I'm going to write those here. You know, I know we already did this, but again, it's good review. All right, so some of the kinematics equations that I feel you should kind of have in your head for this particular chapter is that you can find final position if you know average velocity, initial position, and time. Velocity, you guys starting to remember these by heart by now? And then the long one. I don't know who said that, but I like it because it's the long one. Okay, so these are something that you need to remember because they start to come into play again. All right, so I think we have time to go on to this next quick check really quick. What did I miss there? Basically just some stuff that we've already talked about. And Newton's second law, using kinematics. All right, so this one is showing that the cart is initially at rest. There's a force that's applied to the cart for a certain amount of time, after which the car has speed velocity. So if you're supposing that the same force is applied for the same time to a second cart that has twice the mass, and in this case friction is negligible, afterward the second cart's speed will be what? All right, so this is wanting you to think about those kinematics. If we were using our Newton's second law equation, and again, this is one of those things where it doesn't give you any numbers, so you can kind of I would come up with the simplest numbers possible. I'm just going to give the force and the mass values of 1 so that I have an acceleration of 1 meter per second squared. But then it says the second cart would have twice the mass, but it had the same force, so 1 over 2 in this case. And it wants you to actually figure out the cart's speed. So it said that it was initially at rest. So if you look back at your kinematics equations, which I think I can go back to really quick. Yeah, we could figure that by a couple of ways, but this is the one that I go to because we just found the acceleration, and it did say that it was for the same amount of time. Okay, so we can make up a time. If it was initially at rest, then it was going 0 meters per second. The acceleration in this case, after we changed the mass to twice as much, it was 0.5 meters per second squared. The time, I'm just going to give it as 1 second. Again, come up with the simplest numbers, which ends up giving you 0.5 meters per second, which would then be answer B. Okay? All right, so I am going to stop the video and start again on the next one.